Hey there. We feel it every single day, right? That warmth from a cup of coffee or when you rub your hands together on a cold morning. But have you ever stopped to think, what is heat? I mean, really? For literally centuries, this was a massive puzzle for scientists. So in this explainer, we're going to take a journey. We'll start with an old, kind of intuitive myth and work our way to the fundamental laws that govern all energy, and we'll see how pretty much everything in the universe is always trying to find its balance.
Okay, so to kick things off, just think about this. It's like a two-way street. When it's cold out, you do a bit of mechanical work. You rub your hands together and boom, you get heat. But it works the other way too. A steam engine, for example, takes heat from boiling water and uses that to do work, pushing pistons and turning wheels. This whole back and forth, this conversion between work and heat, well, that's the absolute heart of what we call thermodynamics.
All right, so let's start with that first part of the street, the one we all kind of know from experience, the idea that motion, or, work, can turn into heat.
It's funny how science works. Before we could figure out the right answer, we had to go through a really popular wrong one. And the first big theory about heat was, well, it was super clever, it made a ton of sense back then. There's just one tiny problem. It had a fatal flaw.
So yeah, let's dive into that clever but wrong idea. It was called the caloric theory. And get this, for more than 100 years, scientists were pretty much convinced this was the explanation for heat.
So the analogy here is actually pretty cool. The way scientists pictured it was that heat was this invisible, weightless fluid they called caloric. Think about it like water flowing between two tanks. If one is full and the other is half empty, the water flows until the levels are equal, right? Well, they thought this caloric stuff did the same thing. It would flow out of a hot object and into a cold one, kind of soaking in until everything balanced out.
So, if we boil it down, the whole theory rested on three big ideas. 1. Heat is a substance, a fluid. 2. It always flows from hot things to cold things. And 3, and this is the real kicker, the most important part, it meant that any object had a limited supply of this caloric fluid. You could drain it out, sure, but you could never ever create more of it.
And right there, that's where the theory starts to fall apart. It leads to this big, nagging question. If an object only has a set amount of heat fluid inside it, then how on earth could you get something to produce what seems like an endless supply of heat? That was the paradox, the one question the caloric theory just had no good answer for.
Well, the answer, and the thing that finally killed the caloric theory, came from a really unlikely place. A noisy, busy cannon factory, of all things. And it's all thanks to a guy named Benjamin Thompson, who you might also know as Count Rumford. He noticed something that would change everything.
So Rumford is watching these workers bore out the insides of brass cannons, and he's just blown away by the insane amount of heat this process creates. I mean, enough to boil huge vats of water. But his big aha moment came when he tried using a dull drill bit. See, the dull bit barely scraped away any metal, but it produced even more heat. That was the smoking gun. If the caloric fluid theory was right, then a sharp drill cutting away lots of metal should release more of this fluid, right? But the exact opposite happened. The heat wasn't coming from the metal, it was coming from the work being done, from the friction.
And that led to this revolutionary new idea. Heat isn't some fluid being drained out of an object, no. Heat is a form of energy that's being created by the mechanical work of the drill. And that one simple idea, it just completely shattered the caloric theory and paved the way for the modern science of thermodynamics.
This discovery was a total game changer. The idea that heat wasn't some mysterious fluid, but was actually a measurable form of energy? Wow. It meant scientists could finally stop worrying about invisible stuff they couldn't see and start focusing on things they could actually measure, in the real world, on a big or macroscopic scale. This was literally the birth of a new kind of science.
Okay, so this is a really important distinction to get. You could try to understand heat by looking at the microscopic level, tracking the zillions of individual molecules bouncing around. But honestly, who has time for that? Thermodynamics is smarter. It completely sidesteps all that complexity. It's a macroscopic science. It looks at the big picture, dealing with properties we can actually measure, with gauges and thermometers, stuff like pressure, volume, and temperature. Here's another great way to picture the difference. The science of mechanics, that's all about the motion of the bullet. Its path, how fast it's going, the forces pushing on it. But thermodynamics, it's interested in what's happening inside the bullet. It asks a different question. When that bullet slams into the wood, where does all its energy of motion go? And the answer is, it turns into disorganized internal energy. And how do we measure that? As a rise in temperature, as heat. All right, so we've established that thermodynamics is the big picture science of internal energy. Now, let's get into its most fundamental concept of all, this natural drive that all systems have to find a state of balance. We call that equilibrium.
But first things first, we need to know what we mean by the state of a system. It's really just a snapshot of its condition at any given moment. And we describe that snapshot using 4 key measurable variables: pressure, volume, temperature, and mass. And here's the key. If those 4 things are stable, if they're not changing anymore, then we can say the system has reached thermodynamic equilibrium.
So what happens when you bring 2 different systems together? Well, it all comes down to the kind of wall you put between them. You've got an adiabatic wall. Just think of that as a perfect insulator. You know, like the wall of a really good thermos. It stops heat from getting through. Then you have the opposite, a diathermic wall. That's a conductor. Think of a metal spoon and a hot cup of coffee. It lets the heat flow right through and makes the 2 systems interact. And this is where it all comes together. The moment you connect 2 different systems with one of those conducting diathermic walls, something starts to happen all on its own. Energy starts to flow from one to the other. Their properties, their temperature, their pressure, they all start to change, and they'll keep changing until, finally, they settle into a brand new shared state of balance.
So how do you know when it's all over? What's the one universal sign that the systems have finally reached this thermal equilibrium? It's actually incredibly simple. Their temperatures become the same. That's it. The second the temperature of system A equals the temperature of system B, the flow of energy stops. They found their balance. So let's just do a super quick recap of the keywords. We're looking at the macroscopic world. We use insulating or adiabatic walls and conducting or diathermic walls, all to watch how systems find their way to a stable equilibrium. Got it?
And that last idea, that really simple, obvious fact that temperatures always even out when things are in contact, it's so fundamental, so absolutely basic to everything else, that they call it the 0th law of thermodynamics. And yeah, you heard that right, 0th. They actually came up with the first and second laws before this one, and then realized, wait a minute, this other idea is even more fundamental. Which kind of leaves us with a great question, doesn't it? If that's the 0th law, then what in the world are the first and second?